Hello and welcome to Sleepy Scientist. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight we take a journey not just across space, but through deep time to meet a microscopic life form so small you couldn't see it if it floated on the tip of your nose, yet so powerful it transformed the entire planet. Imagine a world without oxygen, a sky without blue oceans, without fish, and land without trees. A world where the air would choke you, and even the clouds smelled like eggs. This was Earth before a tiny bacterium rose from the ancient seas and exhaled the breath that changed everything. So snuggle in, get comfortable, and let your imagination float through the haze of primordial mists. If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these journeys for you now. Picture it Earth about 3.5 to 4 billion years ago. The sky is murky, maybe red or gray, certainly not blue. The air is thick with carbon dioxide, methane, and ammonia. There's no oxygen, not a whisper of it. Volcanic eruptions are constant plumes of ash rise endlessly from fire-breathing mountains, painting the skies with a palette of danger. Lightning crackles like nature's restless heartbeat. No trees, no grass, no birds, no insects, just barren rock, boiling water, and clouds that taste of sulfur. The oceans, they're not the sapphire expanses, you know. They're greenish, perhaps even a reddish-brown thick, with dissolved iron and chemical soups. The warmth of the young sun glints on oily waves, and beneath the surface something stirs. Even here, life has found a way. The first forms are single-celled, primitive, and anaerobic. That means they thrive without oxygen. In fact, oxygen would kill them. These early life forms float or cling to rocks, extracting energy from sulfur iron and other exotic compounds. They are quiet survivors, learning to live in a world not made for breathing. Have you ever wondered what it would feel like to stand in a world not meant for lungs? A world that had never heard the sound of birdsong or wind in the trees. This was a planet in waiting, waiting for a breath, waiting for change. Now close your eyes and imagine this ancient Earth as an unfinished painting. A canvas of fire and water and gas, but no breath, no color in the sky, no light from within. And somewhere in this dark palette, a tiny brush stroke appears, something small, barely noticeable. It is a single cell, a bacterium, and it has an idea. This microbe is not like the others. While the rest feed on sulfur and metals, this one starts to play with light. Sunlight. It finds a way to capture that energy, using it to split water molecules, and in doing so, releases something no one else wants: oxygen. At first, it's just a trace, a molecule here, another there. The other microbes don't notice. But the bacterium keeps going. Its efficient thriving in the sunlit shallows. It begins to spread, multiply, blanket the sea floor in slippery green mats, early microbial cities known as stromatolites. And with every breath, with every lazy exhale, it releases more oxygen into the ocean. Have you ever thought about how something so small, smaller than a grain of dust, could shape an entire world? Could you, if you were a microbe, imagine the weight of that responsibility? Of course, this little cell doesn't know what it's doing. It's just living, just growing. But the ripples it sends begin to gather. Over millions of years, the oxygen it releases doesn't disappear. It builds up in the oceans, slowly reacting with the iron dissolved there. That iron rusts, falls to the sea floor, and settles in layers. Red bands, silent evidence. The planet begins to remember. And still the sky stays breathless. But not forever. The story is just beginning. This is not a sudden revolution. It is the slowest miracle imaginable. A planet learning to breathe. And it all starts with a single sun-loving cell. You follow that breath now deeper into the water, drifting through the warm, shallow seas of an Earth still wild and raw. The waves roll quietly overhead, and beneath them, a living green haze spreads across the seafloor. These are the cyanobacteria, ancient, shimmering, sunbathing microbes. You might hear them called blue-green algae, but they aren't algae at all. They're bacteria. Simple, tiny, and revolutionary. And they are busy changing everything. These cyanobacteria have discovered something no other life form had mastered: photosynthesis. More specifically, oxygenic photosynthesis, the kind you know so well today. The kind that turns water and sunlight into sugar and oxygen. But for them, oxygen isn't the prize. It's a waste product, an afterthought. They just want energy, and splitting water molecules is their elegant, light-powered solution. The leftover oxygen released into the sea, like bubbles rising from a diver's mask. You float past one of these colonies, and though each bacterium is microscopic together, they form vast, colorful mats, slick, layered, almost felt-like. Stromatolites, living carpets of time. Some of the oldest fossils on Earth are fossilized versions of these very same structures, some over 3.5 billion years old. Yes, the descendants of these cyanobacteria are still here, still making oxygen, still basking in the light. You might wonder, why didn't oxygen build up in the air right away? The answer lies in the water. The early oceans were saturated with dissolved iron, lots of it floating invisibly. And oxygen is highly reactive. As it appeared, it instantly bound with that iron forming iron. Oxides rust and sinking to the seafloor. This kept oxygen levels low in the atmosphere for a long time. The oceans became an oxygen sink, absorbing and storing every breath these tiny bacteria gave off. Imagine painting a canvas, but the paint disappears every time you lift your brush. That's what the cyanobacteria faced. Their gift of oxygen was swallowed by the sea, silently transforming the chemistry of the planet beneath the waves. And yet, they persisted. No ego, no grand plan, just cell after cell dividing, sunning, and exhaling. Over and over, for millions upon millions of years. Isn't it astonishing to think that the oxygen you're breathing now began as a kind of cosmic accident? A side effect of a microbial lifestyle, that every breath you take is a whisper from ancient sunlight, filtered through ancient water, filtered through ancient cells. Let that idea settle softly in your thoughts. This process, the photosynthesis of cyanobacteria, remains one of the most important biochemical reactions on Earth. Even today, more than half of the oxygen in our atmosphere comes from tiny organisms, mostly in the ocean. Phytoplankton, distant descendants of those early cyanobacteria, still carry the torch, still taking light and water and quietly filling the world with breath. There's something poetic about that, don't you think? That it's not towering trees or roaring machines that produce the most oxygen, but the smallest, most delicate things drifting, floating unseen. What does that say about power? What does that say about change? Back in those early oceans, the change is invisible for now. The air is still thick with carbon dioxide. Methane still dominates. The sky, more gray than blue, holds no promise of breath. But the tides are shifting. The iron is slowly being used up. And the oxygen, once instantly absorbed, is beginning to linger. Each bubble rising from a cyanobacterium now has a slightly better chance of survival. Some drift upward toward the surface, some escape. And for the first time in Earth's history, the atmosphere, this thin veil of gases wrapped around the planet, starts to feel different. lighter, sharper, breathable someday. You wouldn't be able to breathe it yet, not even close. But the seed has been planted, and it grows not in forests or valleys, but in puddles, pools, and tide-splashed rocks where ancient microbes sip sunlight and breathe out transformation. The earth doesn't know it yet, but life has found its voice, and it's whispering oxygen. Follow that whisper now as it winds its way through the warm seas and begins to echo louder through the eons. You drift gently above the stromatolite fields like a slow breeze brushing against the surface of deep time and feel the planet beginning to stir. Because the chemistry is changing. Something new is happening. The cyanobacteria are no longer just passengers on Earth, they've become engineers. With every breath, with every bubble of oxygen they release, they are writing a new chapter in the story of the planet. And the chapter is titled Photosynthesis, a Chemical Revolution. This is the moment where the quiet becomes catalytic. When cyanobacteria use sunlight to split water molecules, they produce sugars to store energy and give off oxygen as a byproduct. That one reaction has altered the fate of every organism that would ever live. You can almost picture its sunlight filtering down into shallow waters, golden beams flickering like liquid threads. The cyanobacteria reach for them, greedy and patient, transforming photons into fuel. The process looks calm, even graceful. But behind the calm is a chemistry so powerful it will eventually turn stone into rust, gas into breath, and silence into symphony. Carbon dioxide and water become glucose and oxygen. A little sugar, a little air, nothing dramatic. And yet, it is everything. This marks a sharp divide in Earth's timeline before photosynthesis and after. The oxygen starts to build slowly at first. As it increases, the oceans begin to react. All that iron floating in the water, remember it, dissolved, invisible, restless. It begins to meet its match. Oxygen binds with it, forming iron oxide rust, not just the kind that flutters off an old bicycle, but iron that sinks, that coats the seafloor in layers of red. These are the first signs of the great oxygenation event, but that's still a little ahead. For now, the change is mostly underwater, hidden to the sky. You float gently above it, watching rust fall like snow. Layers upon layers of it settle over time, creating geological formations that will one day be dug up and studied, banded iron formations, dark and red solid echoes of microbial exhalations. Ask yourself this: if you were a bacterium floating in the shallows, could you imagine the consequences of your breath? Could you fathom that the waste you expel would one day give rise to forests and lungs, to birds and music and stories and dreams? Of course not. And yet here we are. You might be wondering, why didn't photosynthesis evolve earlier? The answer may lie in complexity. The version used by cyanobacteria is intricate, involving specialized molecular machines like photosystems. It's possible simpler forms existed first, using sulfur or hydrogen instead of water. But once water became the donor, the byproduct was no longer just benign, it was transformative. Oxygen, you see, is reactive. It doesn't sit still. It binds. It rusts. It burns. It changes things. That's why it's so useful to you now, but in the ancient world it was a volatile newcomer, a disruptor. Still, the photosynthesizers keep going. There's no stopping them. Their mats spread wider. Their bubbles float higher. Their influence seeps into every tide pool and inlet and continental shelf. And above all this, still no blue sky. Still no oxygen to breathe. But the recipe is written, and the ingredients are accumulating. The Earth is preparing for a transformation that will take place not with earthquakes or lightning, but with light and time. Photosynthesis continues, slow and persistent. A chemical revolution in no hurry, trusting that the world will change, molecule by molecule, tide by tide. If you could dip your hand into that ancient water, it would come back coated in the minerals of change. You'd feel the metal taste the difference in the salt. The oceans were never still, not even back then. They were bubbling with the promise of air. You lie back in that thought, now suspended in the hush of prehistory. Let the knowledge swirl around you like a warm current, that everything you breathe, every fire you light, every heartbeat in your chest owes its rhythm to a bacterium that learned how to sip sunlight and exhale possibility. Now let that current carry you forward, slowly, steadily, into the shallows of a rising tide, a tide not of water, but of oxygen. You've seen the cyanobacteria stirring quietly, reshaping chemistry with each breath, and now their exhalations begin to tip the balance. The world is approaching a tipping point, though it doesn't know it yet. The oxygen that once vanished into the embrace of iron has finally begun to saturate the oceans. The iron, once hungry and abundant, is now mostly bound up, sunken rusted into the seafloor in those thick red layers of banded iron formations. The sink is full, and now oxygen is starting to spill over. You might picture it like an overflowing bathtub. At first, every droplet disappears down the drain unnoticed. But as the tub fills, the water rises, and one day that next droplet spills over the edge. And so begins the great oxygenation event, an era when the atmosphere for the first time in Earth's 4.6 billion-year history begins to hold its breath. It's subtle at first. A few free molecules of oxy drifting upward from the sea, breaking the surface tension and rising into the open air. The atmosphere, once dominated by methane, carbon dioxide, nitrogen, and water vapor, begins to make room for something new. And here's where things get complicated, because oxygen, as beautiful as it may seem to you now, was once a toxin. You float through this time, letting the numbers trickle through your mind. Prior to this event, oxygen made up less than 0.01% of the atmosphere. Over tens of millions of years, it climbs slowly, surpassing 0.01%, then 0.1%. Still not breathable to us, but enough to start a chemical revolution in the sky. One of the biggest changes, the destruction of methane. Oxygen doesn't just sit quietly, it reacts, and one of its early victims is atmospheric methane, a potent greenhouse gas that until now has kept the Earth cozy and warm under a thick insulating blanket. With more oxygen, methane levels plummet. And when that happens, the Earth begins to cool. You may find this surprising oxygen making the world colder. But this is the subtle dance of planetary chemistry. The loss of methane ushers in a climate shift, possibly contributing to what's called the Huronian glaciation, one of the earliest and longest ice ages in Earth's history. A global deep freeze perhaps triggered by a microbial breath. You imagine the scene, the same Earth that once boiled and steamed now begins to frost over. Glaciers slide toward the equator. Ice creeps into places that had never known cold, and all of it from breath to blizzard begins with tiny cyanobacteria exhaling in the sun. Isn't that astonishing? That warmth and cold life and extinction. Sky and sea are all tied together by the chemistry of photosynthesis. Now ask yourself, this could a creature so small know it held that kind of power? Could you? But the oxygen doesn't stop. It keeps rising. With the oceans no longer consuming it and the atmosphere no longer able to shrug it off, oxy begins to accumulate in earnest. It binds with volcanic gases. It begins to alter the surface of rocks. It begins to reshape the climate. And beneath the surface in the microbial world, a mass extinction is brewing. Because many ancient microbes, those that thrived in the absence of oxygen, cannot survive in this new air, it is poison to them. Their enzymes collapse, their membranes fall apart. Oxygen seeps into every niche, every crack, every tide pool, and begins to smother the life that had ruled the planet for billions of years. But you'll hear more about that soon. For now, you rest at the edge of this invisible tidal wave. The moment before the sky changes color. The moment before life must evolve or perish. And all of it, every molecule traces back to a green shimmer on the seafloor and a sunlight-fueled breath from a cell smaller than the width of your hair. From silence to symphony, from sulfur to sky, the oxygen has arrived. Now drift closer to the consequence, gently like falling ash settling on still water. The world has changed, and not all its inhabitants are ready for it. What began as a breath has become a flood, and many of the Earth's early residents are about to be swept away by something they never saw coming: oxygen. You may not think of air as dangerous, but to the life forms that thrived in the early anoxic world, meaning without oxygen, this new gas is toxic. Highly reactive, it tears through cells, oxidizing molecules, breaking delicate bonds, damaging DNA. It's as if the planet's chemistry has turned hostile. The cyanobacteria, those quiet photosynthetic architects, have unknowingly triggered the Earth's first mass extinction. You hover now over a seafloor, once thick with microbial colonies, strange and thriving. Many of them are anaerobic, meaning they evolved to live and reproduce in oxygen-free conditions. Their enzymes, their very metabolism was built for a world without this sharp new molecule. But now oxygen is seeping in. At first it creeps quietly into the upper layers of water. A few cells die here, a few there. But over thousands of years, the oxygen doesn't go away. It builds layer by layer, saturating more of the ocean's depth, climbing higher into the atmosphere. One by one, entire populations of anaerobes vanish. Silent die-offs, invisible extinctions, no bones to fossilize, no cries to record, just the subtle absence of what was once abundant. The irony is hard to miss. A molecule that will one day sustain whales and forests, fill human lungs and light campfires, begins its reign by wiping out almost everything that came before. Can you imagine that gift that's also a weapon? A breath that suffocates? But evolution is nothing if not adaptable. And in the face of this chemical pressure, new life forms begin to emerge. Some microbes develop antioxidant enzymes, proteins that can neutralize oxygen's chaos. Others retreat to oxygen-free niches, deep sediments, hydrothermal vents, underground pockets where the old world lingers. Still others do something astonishing. They learn to use oxygen. Yes, where one creature sees poison, another sees power. Oxygen, after all, is efficient. It enables a cell to extract far more energy from food than anaerobic respiration. Nearly 19 times more. That's like switching from a flickering candle to a blazing furnace. These new microbes begin to thrive in the oxygenated zones, harnessing the chemical fire in their environment. They are the ancestors of what will eventually become life forms that breathe. In the broader view, you're watching a massive planetary reshuffle. The players are microscopic, but the impact is global. Ancient lineages disappear, new ones rise, and through it all the cyanobacteria continue to exhale, indifferent to the upheaval their breath has caused. What does it mean to change the world without trying? What would it feel like to shape the future without knowing you're doing it? Let those questions swirl in your mind like oxygen dissolving in seawater. They are soft but deep. And while the great oxygenation event doesn't leave dramatic fossils, it leaves chemistry. Traces of oxidation in rocks, shifts in isotopes, evidence etched into stone that life turned a corner here. You might wonder, how long did this extinction take? It wasn't an afternoon or even an era. It was a drawn-out transformation. Perhaps 100 million years or more. Long enough that the cyanobacteria likely had no sense of it. But in that vast time, the stage was cleared. The Earth became something new. The old world passed away in silence, and a new one filled with breath and potential quietly began to take its place. You float above it all now, this slow and graceful catastrophe, knowing that from the ruins of a world without air, something wonderful is about to rise. A world that breathes. The Earth has wept its rust into the oceans, silenced much of its ancient, breathless life, and now slowly it begins to look different. You rise gently through the thickening air, through wisps of gas that are no longer just carbon dioxide and methane, but now increasingly oxygen. And suddenly, something subtle shifts in the sky. You don't see it immediately, but then you notice the sky has turned blue. It wasn't always this color. Imagine, if you can, standing on a lifeless hill 3 billion years ago, and looking up, not at the calm azure dome we know, but at a heavy, hazy veil of reddish-brown or even greenish-gray. Back then, sunlight was filtered through thick greenhouse gases, and without oxygen, there was no scattering of blue light. But oxygen brings clarity. Specifically, when enough oxygen collects in the atmosphere, it reacts with ultraviolet light from the sun and starts to scatter shorter wavelengths, blues and violets, in all directions. Your human eyes are more sensitive to blue, so that's what you see. A soft, infinite dome, like a shallow bowl filled with sky. It's breathtaking, isn't it? That the very molecules released by ancient microbes not only transformed the oceans, not only changed the chemistry of rocks, but painted the sky itself. And there's more. That rising oxygen now reacts with ultraviolet sunlight in another even stranger way. It begins to form ozone, a molecule made of 3 oxygen atoms instead of 2. And it doesn't form just anywhere. It forms high above the Earth in the stratosphere, where the sun's UV rays strike the fresh oxy molecules and split them apart. Those freed oxygen atoms then collide with intact oxy, joining up to form ozone. And ozone has a gift of its own. It absorbs harmful ultraviolet radiation. Without it, UV light would bombard the surface, damaging DNA, tearing apart cells, making it nearly impossible for life to step out of the oceans. So while cyanobacteria never planned it, their photosynthetic breath ends up weaving a shield around the planet, invisible but essential. A molecular guardian. Can you picture it? This delicate layer floating far above your head, stretched thin but strong, absorbing rays that could harm, filtering sunlight into warmth and safety. A kind of planetary sunscreen made from microbial size. The Earth is no longer just rock and ocean. It's becoming wrapped in a biosphere, a breathing world, a living sky. But change is never without cost. The methane-rich atmosphere that once trapped heat is now mostly gone. With oxygen oxidizing methane, the planet likely entered a cold spell, a period of global glaciation. Some scientists believe this may have been the first snowball Earth, when ice crept toward the equator, blanketing much of the planet in white. Imagine standing at the edge of a frozen sea that stretches farther than you can see. Above, the sky is blue at last, but the warmth has fled. The gift of oxygen brings clarity and color, but also cold. Isn't that often how change works? We ask ourselves, what is the cost of clarity? What must fade for something else to shine? Yet even in the chill, new possibilities open. The ozone layer shields the surface, allowing the land above water to become safer. Light filters in gently. Shadows form where there were none. The foundation is set for future life to leave the oceans. But for now it waits. The sky, now blue, reflects on oceans that are still iron-tinted, still in transition. The wind stirs molecules not yet tuned to lungs, and the descendants of the ancient anaerobes cling to deep, dark corners, huddled in the last refugees from the breath that changed everything. Breathe in slowly now. Let the idea settle in your chest that the color of the sky, the boundary of the sea, the gentle sun you feel on your skin, all of it rests on the shoulders of organisms smaller than dust. You can't see them, but they're still with you, drifting in the oceans, in lakes, in puddles, still catching light, still releasing breath, still keeping the planet blue. And now you sink downward gently toward the seafloor, not through today's clear blue ocean, but into ancient waters, murky and heavy with secrets. You're gliding back to a time long before coral reefs or fish-filled shoals. What waits below is not colorful life, but stone. And not just any stone that remembers. You land softly on a ridge of layered rock, dark gray and rust red, alternating like pages in a geologic diary. These are the banded iron formations, and they are the silent witnesses to one of Earth's grandest transformations. They tell the story of a world being rusted from the inside out. These rocks formed long before air was breathable. In Earth's ancient oceans, iron floated freely in its reduced soluble form, Fe2+. It was invisible, dispersed throughout the sea, like salt in soup. But when oxygen began to appear first in whispers, then in waves, it encountered that iron and changed it, oxidized it into Fe3+, and the oxidized form is no longer soluble. It precipitates, falls like mineral snow, and settles onto the ocean floor. This happened over and over again, in pulses, in layers, dark bands of silica or shale when oxygen was scarce, red bands of iron oxide when oxygen surged, back and forth, over and over. It's almost like the Earth was breathing in long, slow gasps. You might wonder, how long did it take to build just one of these layers? Decades, centuries, millennia, layer upon layer, molecule by molecule. This wasn't a sudden paint job. It was the quiet artistry of chemistry, crafted by sunlight, water, and microbial breath. Some banded iron formations are over 2.5 billion years old. Others stretch across entire continents: Australia, Canada, South Africa, Greenland. Massive, silent, and motionless, yet telling the same story that once the oceans bled iron, and cyanobacteria came to turn that blood into rust. Let your fingers trace the rock in your mind. It's smooth in places, rippled in others. The red layers are like sleeping embers, still warm in a metaphorical sense, because they speak of a fire that was just beginning to smolder across the planet. Oxygen metabolism. You ask yourself, could a rock be a fossil of breath? Could a color remember a chemical change? The answer is here beneath your imaginary hands. These rocks are not just mineral, they're messages. Messages from a time when oxygen was new, strange, even dangerous. But they also signal a threshold. As the iron in the oceans was gradually used up, rusted out, sunk, solidified, there was less for oxygen to bind to. And so the oxygen began to escape. No longer held in chemical chains, it bubbled upward, leaving the oceans behind and entering the air in earnest. And once it did, everything above the surface began to feel its presence. Rocks on land started to oxidize, reddening, cracking, weathering differently. Minerals that once formed in anoxic conditions were replaced with new oxygen-dependent varieties. Even soil began to evolve. It became richer, more reactive, more ready to support complex life. The transformation was planetary, and the banded iron formations are its exhale frozen in stone. They also marked the end of an age. Eventually, the dissolved iron was mostly gone. Oxygen had no more ocean to bind with. The rusting slowed, and with that banded iron formations stopped forming like a pen being gently set down after a long letter. That geological silence, no more red bands, tells us that oxygen had finally broken free. And so the sky turns bluer, the oceans shift in tone, and the stage is prepared for new kinds of organisms to emerge. Organisms that no longer fear oxygen, but embrace it. For now, though you rest among the ancient red layers, the rusted memory of Earth's first chemical rebellion. A rebellion led by sunlight, water, and the tiniest architects the world has ever known. Let your breath slow your mind quiet and listen. If rocks could sigh, this one would whisper to you, I remember when the planet learned to breathe. Now gently rising from the rusted archives of the seafloor, you drift back toward the shallows, toward the light. The earth has changed inside and out. The sky is blue. The seas are calmer, oxygen-rich. The banded iron formations have ceased, a geological pause. And in that pause, evolution listens and answers. Because now something astonishing begins the rise of aerobic life. You float beside a single-celled organism, newly adapted, freshly evolved, not a cyanobacterium, but one of its distant neighbors. A primitive prokaryote, once anaerobic, now equipped with a novel metabolism, aerobic respiration. Unlike fermentation or other oxygen-avoiding techniques, this cell is bold. It takes oxygen in, invites it to the heart of its chemistry, and uses it to ignite its food from within. Think of it like switching from a campfire to a fusion reactor. The oxygen allows for an explosion of efficiency. One molecule of glucose, when burned with oxygen, produces up to 38 ATP. That's the energy currency inside all living cells. Anaerobic respiration only yields 2. This new system gives cells the power to grow larger, to move more, to become more complex. You might ask, how does one tiny innovation reshape the future of life? Because energy is everything. With more energy, cells can specialize. They can evolve new functions, new structures. They can afford to take evolutionary risks. Aerobic respiration becomes the engine of complexity, the unseen force that pushes biology towards something it's never done before. Toward eukaryotes. These are the cells that make up you and everything you see, eat, or touch that isn't a microbe. Trees, fish, birds, fungi. Even your own breathy thoughts, they all trace back to the first eukaryotic cells, which appeared around 2 billion years ago. And here's where it gets wonderfully weird. Scientists believe that eukaryotes began when one primitive cell engulfed another, a kind of merger. Instead of digesting it, they formed a partnership, a symbiosis. The swallowed cell became a mitochondrion, the powerhouse of the modern cell. And it just so happened to be an oxygen user. Yes, the mitochondrion is likely the descendant of an ancient aerobic bacterium. You carry its DNA inside you today, tucked into the cells of your heart, your brain, your fingertips. You are in a very real way a colony of merged organisms forged by the oxygen revolution. Isn't that beautiful? That your every heartbeat is powered by an ancient flame lit billions of years ago by tiny breathers of sunlight. The rise of aerobic respiration doesn't just power evolution, it transforms what's possible. Organisms can now grow bigger, survive longer, move faster. It's not the end of the microbial world, not by any means, but it is the beginning of life as you recognize it. Multicellularity is now within reach. So is complexity. So is thought. And through it all, the cyanobacteria are still at work, still breathing, still feeding the system. But now they're no longer the only ones transforming the planet. They've become the foundation on which the new world is built. Let yourself imagine the moment when one cell swallows another, and the two become one, a quiet molecular handshake. No explosion, no sound, just a shift. But it ripples forward through time, through the evolution of animals, of primates of the breath, rising now in your own chest. Ask yourself, how many quiet partnerships have built the world you see? How many invisible choices shape the visible future? The answers linger in your breath, in your cells, in the stars themselves. The earth is no longer just a place where life clings to stone. It's a place where life builds itself from life. You drift now through time again, letting the aeons slip past like clouds across a pale sky. The earth is breathing more steadily, more boldly. Oxygen fills the oceans, paints the rocks, sharpens the sky. But now something extraordinary stirs beneath the surface. The world is preparing to take its next evolutionary breath, multicellularity. You're still small here, suspended beside cells in the water, no longer just solo wanderers, but collaborators. They've begun to work together. Cells that once floated alone now stick, sometimes in clumps, sometimes in chains. It starts as an accident, a division where the daughter cell doesn't drift away. But over time, these accidents begin to bring advantages. A cluster of cells can share nutrients more efficiently. They can shield each other from danger. If one cell detects a threat, others might benefit. They can even specialize. One cell focuses on movement, another on absorbing food, another just watches. It's the earliest hint of something breathtaking division of labor. Ask yourself, when does a group of cells become a body? Where is the line between many and one? You drift alongside a colony of ancient algae. They look like shimmering snowflakes, delicate and translucent. Each cell is independent, yet linked, pulsing with energy. These are not yet animals or plants, but they are prototypes of both. The oxygen-rich environment is what makes this possible. Aerobic respiration provides enough energy to support these growing alliances. With more power, evolution has room to experiment, to try out limbs and leaves, spines, and eyes, lungs, and light-sensing pigments. You're watching life become architecture. Structures begin to rise out of cooperation cells, arranged into tissues, tissues into organs, organs into systems. Some organisms stretch upward, reaching for sunlight. Others flatten against the seafloor, soaking in nutrients. Some begin to move, gliding, twitching, swimming through currents, like notes in a song. Fossil evidence from Gripania, spiralice, an ancient coiled alga, nearly 1 billion years old, suggests that multicellular life was slowly taking root. A body over 1 centimeter long, enormous by microbial standards, and it existed because the oxygen allowed for it. That same oxygen also brings defense. Some multicellular creatures begin producing toxins, molecules meant to ward off invaders. Others grow harder shells. Competition is rising. Life, as it gets more complex, becomes more intense, but also more beautiful. Patterns begin to emerge, spirals, branches, stars, lattices. Structures built not just for survival, but seemingly for elegance. Perhaps that's projection. Or perhaps nature always leans toward artistry when energy flows freely enough. Let yourself imagine this world, warm tidal flats, colonies of tiny red and green organisms forming carpets on the seafloor. Some flicker as they move. Others glow faintly in the dark, using bioluminescence to communicate or simply to exist in beauty. The air above them is no longer hostile. It holds possibility now. The ozone layer protects, the blue sky beckons, and life keeps reaching. You ask again, when does cooperation become identity? When do many cells stop being neighbors and become self? There's no single answer. But over millions of years, those little colonies evolve into creatures that could no longer survive alone. Their cells are no longer separate individuals, but parts of a greater whole, a multicellular being, a body. You're one of those bodies. You are made from trillions of once independent cells that now breathe, feel, and remember as one. Your heartbeat is a chorus. The origin of that chorus was oxygen. That invisible thread still winds through you, whispering, connecting, igniting. The same breath that changed the seas now fuels your thoughts. It's all part of the same long story, a planet learning not just to live, but to organize, to compose, to become. Float now into a time of shadows and light into the Proterozoic, where life, newly multicellular, is beginning to leave whispers in stone. The earth is still quiet in some ways, but beneath the stillness, something is stirring. Forms are becoming visible, structures are emerging, and for the first time, biology begins to cast fossilized echoes. You drift over the seafloor of nearly 600 million years ago, and there, soft as brushstrokes, you see them, the Ediacarans. They are the first macroscopic, complex life forms we've ever found in the rock record. Soft-bodied, alien in shape, some resemble quilted pillows, others look like spirals, ferns, or coins pressed gently into wet clay. Some lie still absorbing nutrients. Others may have moved ever so slightly across microbial mats, drifting with currents, or rippling their tissues in ways we can only guess. The ocean here is different now, brighter, enriched. The oxygen that began as a whisper has reached critical thresholds. Atmospheric oxygen has climbed above 1 to 2%, maybe more. Not yet the 21% you're breathing now, but enough to support larger, more demanding bodies. The Ediacaran Sea is Earth's first soft symphony. These creatures don't yet have hard parts, no shells, no claws, no teeth. But they are visible. You wouldn't need a microscope to see them. They stretch centimeters long, sometimes even half a meter. They bloom on the seafloor like ghostly gardens, silent but significant. This emergence is only possible because oxygen allows it. It fuels more than energy. It enables size, and with size comes complexity, new strategies, new structures, new possibilities. But still, it's delicate. One drop in oxygen levels, one shift in chemistry, and these early giants vanish from the record. We still don't know exactly what they were. Were they animals? Something else entirely. Some might be early forms of jellyfish or related to sponges. Others are in a category all their own. But what matters most is this: life is testing boundaries again. Ask yourself, how does a creature without eyes find its place in the world? How does a being without a brain still shape the future? Perhaps by existing at all. The Ediacarans leave more than fossils, they leave questions. And those questions ignite curiosity that most human of traits. As you float through this alien sea, ask yourself what it means to be visible in a world that was once invisible. What it means to become a shape in the sediment, a memory in the stone. Even now, scientists debate how these creatures fed, moved, reproduced. Some may have absorbed nutrients directly from water. Others may have filtered particles. All were fragile, relying on stable oxygen levels to survive. They are, in a way, the first oxygen artists, sculpted by air they could not see, dependent on breath they could not make. But the Earth is not done evolving. Soon, harder-bodied organisms will arrive. Skeletons, shells, teeth, claws. The Cambrian is on the horizon, and with it, an explosion of form and function. But that story comes next. For now you rest among the first large living beings this world has known. Their presence is gentle, their shapes strange but serene. They do not roar or rage or conquer. They exist, and that is enough. You imagine walking barefoot along the shallow's toes, sinking into microbial mats, brushing against frond-like creatures that sway with the current. The light above is dim and diffuse, filtered by clouds and time. But it's enough. The earth is ready now. The air holds the charge. The future is about to bloom. Now quietly the stillness begins to shiver. The delicate Ediacaran world fades, and a new age rises with a burst of movement, of noise, of innovation. You are drifting forward again, brushing into the early days of the Cambrian period, some 541 million years ago. It's not a sudden explosion, not really, not like a bang. But in evolutionary terms, it might as well be. In the blink of a geological eye, the oceans go from whisper to orchestra. Oxygen, still the unseen artist behind the curtain, has reached a new high, possibly around 10 to 15% atmospheric concentration. And with that, something ancient life could never afford suddenly becomes available: experimentation. Let yourself sink into a reef, alive with possibilities. You float beside creatures with shells, spines, eyes, legs. Trilobites scuttle beneath you, armor-plated, multi-eyed, some only the size of your thumb, others as long as your forearm. Wiwaxia glides over the seafloor like a shaggy slipper, its back covered in leaf-like scales. And just ahead, the alien yet elegant Anomalocaris, with swirling grasping arms and a disc-like mouth, swims with unsettling grace. This is evolution on high speed. Why now? Why here? The answer, still softly glowing behind it all, is oxygen. To grow muscles, to maintain nervous systems, to sustain vision, these require aerobic energy. Vision alone is costly in metabolic terms, and yet the Cambrian seas are filled with new eyes. Simple eyes, compound eyes, eyes that can detect shadow or color. Eyes mean predation. Predation means defense, and defense means armor, speed, cunning. It's an arms race, and oxygen is the fuel. Ask yourself, what would life look like if energy were no longer scarce? What strange and beautiful things might evolve if cells could dream a little bigger? In this oxygen-rich sea, life builds machines out of flesh. Muscles pull levers made of bone. Jaws slice, pinch, and crush. Bodies become missiles, traps, decoys. Creatures burrow, dart, climb, and camouflage. For the first time, behavior becomes a kind of tool. And with this Cambrian blooming, we see the roots of everything that will come later. Most of the basic body plans, called phyla, appear here. Mollusks, arthropods, annelids, chordates. You begin to recognize the architecture of modern life. The first notochords appear, flexible rods that will one day evolve into spines. These are the earliest cousins of vertebrates, of fish, of mammals, of you. You might not feel it in the water now, but a current is forming a line of descent, stretching all the way to the fingertips that rest gently near your cheeks as you fall asleep. And yet the Cambrian isn't only about competition. It's also about variation, the sheer creative force of evolution, unbound. Many of the creatures you see here will go extinct, their designs too strange, too narrow, but others will seed entire dynasties, lineages that stretch across the continents, through ice ages, and fire through chance and catastrophe. Let your thoughts swim now in this warm, teeming ocean. You hear the flick of fins, the soft scrape of a trilobite's armor against rock. Light filters down from above, dappling the ridges of sponge-like structures. And in every corner of the sea, cells powered by oxygen are constructing possibilities. Isn't it strange that one bacterium billions of years ago exhaled a molecule that would in time make eyes possible, that would enable flight memory music? The Cambrian explosion is often celebrated as biology's grand debut. But what made it possible wasn't just evolution, it was atmosphere, chemistry, breath. That subtle shift, once invisible, now bursting into form. And even as you float through this crowded reef, there's something else approaching something even greater. Because life is about to take its first steps onto land. You rise now from the oceans slowly, like the first brave explorers of old, toward a world that has never known footsteps. The Cambrian seas still glitter below you, but above lies untouched land, stretching wide and quiet beneath a pale sky. For billions of years, it has stood still. No rustle of grass, no chirp, no buzz, only wind and stone and sun. And then the edges of life begin to creep. Not fast, not loud, just quiet, persistent motion. It starts with algae and cyanobacteria spreading in wet mats along the shorelines, coating rocks, building a bridge between sea and land. These aren't explorers. With legs or eyes, they're patient colonizers, using moisture, light, and time. They form thin films on bare stone, changing the chemistry of the surface beneath them, and releasing once again oxygen. You might ask, what does land smell like before trees? What color is a world without soil? The answer is strange, a chalky dust, a lifeless beige. No brown loam, no black earth. Soil, as you know, it doesn't exist yet, it must be built. And that building begins with microbes. Somewhere between 500 and 400 million years ago, plants begin to rise from those algal mats. First, it's simple, liverwort-like things. Flat, spongy, clinging low, then mosses, then ferns. Slowly land begins to green. But green isn't just pigment, it's chemistry. It's photosynthesis now moving beyond the ocean. These new plants, like their cyanobacterial cousins, breathe in carbon dioxide and exhale oxygen. Only now they're doing it from the continents. And what a change that brings. Atmospheric oxygen levels rise further, creeping toward 15%, maybe more. And with that, life can follow the plants inland. But to do that, it needs tools, lungs, limbs, skin that doesn't dry out in the sun. And so the invertebrates arrive. Picture it, ancient millipedes a meter long, inching their way across damp forest floors. Scorpion-like creatures with claws the size of your hand. These are the first animals on land arthropods that crawl, breathe, and hunt above the tide. Their exoskeletons made from chitin help keep moisture in, and they too are powered by oxygen. The bigger the insect, the more air it needs. And in this ancient atmosphere, thick with oxygen-rich breath, some grow enormous. There's Meganeura, a dragonfly with a wingspan over 2 feet wide. There's Arthropleura, the largest land-dwelling invertebrate ever discovered, stretching up to 2.5 meters long. It rustles through the ferns like a living subway line. And all of this is possible because Earth is breathing deeper now. Oxygen doesn't just power muscles. It enables metabolism fast enough to escape predators, to climb, to fly. It supports the evolution of hearts of lungs, of the complex circulation systems that carry nutrients to far corners of the body. It supports scale. Ask yourself, how tall would you grow if air never ran short? How far would you roam if each breath gave you more than you needed? Now pause for a moment. Look back down at the ocean where vertebrates are evolving. Fish strong and bony with lobe fins that will eventually become limbs. Some of them are preparing to come ashore. You see the first hints in Tiktaalik, a creature with scales and gills and wrist-like bones in its fins. It hauls itself onto mud flats, rests its belly in the sun. It breathes both water and air. It is a bridge between worlds. Life is now writing a new chapter on land in light. Forests begin to grow. True roots tunnel into the rock, breaking it down into minerals, creating real soil. Leaves rise higher, chasing sunlight. The carbon dioxide drawn down by plants triggers another cooling, another shift. And all the while, oxygen builds. It's around this time, some 350 million years ago, that Earth becomes a green-blue jewel from space-lush continents, sparkly seas clouds trailing over mountain ranges never touched by feet. And life so long confined to the sea now touches sky and stone. Still powered by a breath first exhaled by microbes in ancient tides. Still following a path lit by invisible molecules. Still unfolding. You wander now through forests older than memory, giant club mosses, towering tree ferns, and spiny horsetails reach toward the clouds. It's the Carboniferous period some 300 million years ago, and the world is thick with green. The air is warm, the swamps endless, and oxygen. Oxygen is abundant far more than today. You take a deep breath here in this prehistoric wetland, and it's richer, thicker. Oxygen levels are believed to reach 30–35% of the atmosphere, far higher than your modern 21%. That changes everything. It makes giants. All around you, insects balloon to sizes you'd never imagine. That massive shape gliding above the ferns, that's Meganeura. The dragonfly you met earlier, its wings brushing tree fronds as it soars by, riding the currents like a silent hang glider. Its modern descendants are delicate hand-sized, but in this hyper-oxygenated world, it grows to nearly 70 centimeters across. Over there, millipedes the length of canoes slither through leaf litter, their hundreds of legs a soft rustle on the forest floor. Their exoskeletons don't collapse under their own weight. Oxygen fuels the respiratory systems that make their vast bulk viable. Ask yourself, would your lungs need to work as hard in a world like this? Would you feel lighter, more powerful, if every breath gave you more than enough? Even fire behaves differently now. With so much oxygen in the air, wildfires are easier to ignite and more difficult to stop. Lightning strikes forests like a match to kindling. Whole groves go up in flame. But even this is part of the balance. Fire clears the underbrush, returns nutrients to the soil, opens gaps for new growth. The forests are self-renewing, cycling through life-death and rebirth, all under the breath of oxygen. Now drift through the swamplands of the equator. The continents haven't yet taken their modern shapes. Instead, they cluster close, forming tropical superswamps that trap organic matter, dead plants, fallen trees, ferns buried in still waters. Over time, this buried biomass becomes coal, compressed by sediment and time. These forests are writing energy into stone. Hundreds of millions of years later, humans will dig it up, burn it, reshape civilizations with it, but now it simply lies there, quiet, waiting. Meanwhile, deeper in the forests, a change begins. Some amphibians begin spending more time on land. Legs grow stronger, lungs more efficient. Scales thicken. And soon, reptiles are born. Reptiles carry their water inside them. Their eggs are amniotic with protective shells and internal sacs. They don't need to return to the water to reproduce. They can live inland in drier places. They become the first true terrestrial vertebrates, free from the pull of the sea. And oxygen makes their journey easier. More oxygen means higher activity levels. Higher activity means new behaviors, predation, escape, courtship territory. Life is getting not only larger, but more expressive. Ask again if your ancestors could move farther, faster, feel more. How did oxygen shape who you are now? What parts of your nature were born in forests long turned to coal? This period, lush and wild, doesn't last forever. Shifts in the Earth's tilt, in carbon dioxide, in weathering of rocks, these slowly bring a cooling. Swamps dry. Oxygen levels begin to fall. The Carboniferous ends, but its legacy is profound. It creates the fossil fuels that will one day reshape human history. It gives rise to reptiles that will lead to mammals and dinosaurs. It proves that oxygen doesn't just support life, it can transform it, elevate it, embolden it. Now, as you stand among towering trees with fronds wide as sails and bark like armor, you feel the thrum of an ancient heartbeat, slow, steady, strong. The world is alive, exhaling, changing, and life always is listening. Now step carefully because the earth has begun to tremble again, not with footsteps, but with extinction. The world that oxygen built is entering a time of shadows of endings. You find yourself near the close of the Permian period, roughly 252 million years ago. Forests still rise, animals still move, but change is coming swift and deep. The continents have collided into a single massive supercontinent, Pangaea. Vast deserts stretch across the interior. The oceans, once warm and well oxygenated, now struggle with stagnation. Temperature fluctuations, volcanic eruptions, and methane releases all converge. And then the worst extinction Earth has ever known. We call it the Great Dying. It's not a sudden event, not a bang, not a moment. It's a slow unraveling. Over the course of perhaps 60,000 years, over 90% of marine species vanish. About 70% of land vertebrates go with them. Coral reefs disappear. Whole ecosystems collapse. Even the bugs, usually hardy, persistent, suffer massive losses. You drift through a sea where oxygen has become scarce. The oxygen-rich paradise of the Carboniferous is gone now. Atmospheric oxygen levels may have dropped to around 12%, perhaps even lower. Some parts of the ocean become anoxic, devoid of oxygen entirely. In these black, suffocating waters, few things survive, and so life contracts. Ask yourself, what does it feel like for a planet to struggle to breathe? What kind of world grows quiet, not from sleep, but from exhaustion? Much of the devastation is thought to stem from enormous volcanic eruptions in what is now Siberia, flood basalts that release carbon dioxide into the atmosphere. Global temperatures rise by 5 to 10 degrees Celsius. Oceans acidify. As warm water holds less oxygen, marine life gasps for breath. But it's not the end. You drift now to the survivors, those strange, sturdy species that make it through. Small reptiles, burrowers, opportunists. The ones who can weather long droughts, who don't need much air, who live in crevices and wait for better days. These become the seeds of life's next chapter. Oxygen, though depleted, begins to rise again slowly over millions of years. And with it comes something new, something massive, something with scales, with teeth, with thunder in its stride. Yes, dinosaurs. They emerge not in the lush, carboniferous world, but from the ashes of catastrophe. They find a planet that's recovering, a stage being reset, a sky breathing deeper again. And they thrive. The Mesozoic era begins the age of reptiles, and once more oxygen becomes a key player. Atmospheric levels fluctuate over these millions of years, likely reaching up to 26% during the Jurassic and early Cretaceous. This allows for not just big bodies, but high metabolism. Dinosaurs are no sluggish swamp creatures. They're agile, active, warm-blooded. Some even sport feathers. Some chase prey. Others take to the skies. You float alongside the pterosaurs with wingspans over 30 feet, gliding on thermal updrafts. Above forests and seas, they soar lightweight yet vast. Their flight, like that of the giant insects before them, is made possible by oxygen. Thin air could never carry such giants. Below dinosaurs like Argentinosaurus, up to 100 feet long, walk across fern-filled plains. They carry the same molecular legacy as you cells breathing in energy, bursting forth, life pushing upward. Ask yourself, is size the ultimate measure of life's ambition, or is it persistence? Adaptability, the ability to begin again. The Mesozoic marches on. Dinosaurs diversify. Mammals hide in the underbrush. The world grows green again. And oxygen, like a careful curator, decides what kinds of life can flourish. But eventually, even the reign of giants must end. You can feel the air thicken with tension, like a hush before a storm. And far across the cosmos, a rock is hurtling through space. A final punctuation mark draws near. And now, the sky burns. You're hovering above the lush, humid forests of the late Cretaceous, vibrant, teeming alive. Dinosaurs thunder across plains. Birds trill and swoop between towering conifers. Tiny mammals scurry beneath ferns. Life hums with complexity and color. Then a flash, a silence, a shockwave. An asteroid, perhaps 10 kilometers wide, strikes what is now the Yucatan Peninsula with a force equal to billions of atomic bombs. It punches a hole into the earth, igniting fires, heaving tsunamis, darkening skies. Dust and soot blanket the atmosphere. Sunlight fades. Global temperatures plummet. Photosynthesis halts. Food chains collapse. And in the span of months to decades, nearly all non-avian dinosaurs disappear. It's the end of the Mesozoic and the beginning of another long breath. You drift through this aftermath ash, drifting like snow forests, smoldering oceans, cooling silence, where once there was sound. And you feel it again, oxygen, that invisible lifeline, is threatened. Fires consumed it. Plant die-offs reduced its production. The air feels thinner. But still it is here. And that is enough. Because down beneath the ferns and buried roots, life is stirring. Not massive anymore, but small, adaptable. A new caste of creatures emerges: birds, insects, mammals. Some mammals, now unshackled by towering dinosaurs, begin to explore. They diversify. Some grow larger, take to the trees, develop sharper senses. Brains expand, limbs change, fur thickens, and oxygen. It climbs once more. Atmospheric oxygen stabilizes between 19-21%, where it remains for much of the modern era. That's the air you breathe now, the breath that flows through your lungs, your blood, your fingertips. A blend perfected through billions of years of photosynthesis, respiration and extinction, rebirth. Ask yourself, is this the world oxygen dreamed of building? What stories do your cells still whisper from their microbial past? Because the story doesn't end in fire or ash. It continues in you. Your cells, descendants of those first cyanobacteria, still carry mitochondria, once free-living bacteria themselves. Your blood binds oxygen with hemoglobin, a molecule adapted through deep evolutionary time. You inhale, and with that simple act, you connect to everything that has come before. Now look around you. Trees breathe with you. Leaves take in your exhaled carbon dioxide and return it as life-giving oxygen. Every breath you take is shared, cycled, ancient, profound. The oceans still shimmer with plankton-silent oxygen factories. Forests still rustle with the invisible work of molecules, carbon and light. Even the soil under your feet teems with bacteria unseen but essential. This planet, the only one we know, wrapped in a thin envelope of breathable air, is a monument to the tiny bacterium that once exhaled for the very first time, and to all the life that followed. You lying there wrapped in warmth and thought are made of that story. Your heartbeat is an echo of ancient tides. Your dreams perhaps are oxygen's way of remembering the stars. Let them carry you now gently. Let the molecules soften, the images fade. The sky is blue, the world is green, and the earth is still breathing. Let your breath slow now. You've traveled across billions of years, from the hush of a silent sea to the rustle of leafy canopies, from the tremble of the first oxygen bubbles to the deep, steady inhale of your own lungs tonight. The air you breathe is ancient. It has spun through time, through coral reefs, and dragonfly wings, through fire and ash and mammalian lungs. Let that thought settle over you like a blanket. Oxygen, once a whisper, has shaped every part of the world you know. It lingers in the moss between stones, in the sigh of wind through trees, in the rhythm of your own chest. It is quiet now, gentle, patient. Close your eyes if you haven't already. Let your thoughts soften into shapes, swirling galaxies of cells, and stories of tiny bacteria dreaming of blue skies. You've wandered far, and there's nowhere else you need to be. Nothing more you need to do. Not right now. Just rest. Let your breath come easily, and as it does, know that you're still part of that same great journey. Life still unfolds, oxygen still flows, and in this moment, you're enough. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know, where in the world are you listening, from what time it is there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Good night, sweet dreams.